In this series of videos, we're talking about the PID algorithm. We started off first understanding what the error is. What are the attributes of the error? The duration, the magnitude, and the rate of change. Then we talked about the definitions of proportional, integral, and derivative. Remember what proportional is designed to do? Is to stop the changing error. Is its goal to make the error zero? No, its goal is to stop the changing error. Integral is designed to make the error zero, but it's too slow by itself. Derivative is designed to stop the rate of change, the slope, but that's not used ever by itself. It was when we went over the interactions of proportional, integral, derivative that you started to see the power. You got the proportional kick and the integral action, and we introduced this concept of a rate or a reset time or a repeat time. It's how long does it take to repeat the original proportional request. That definition of repeat time really only applies to one of the forms of the PID algorithm. It just makes sense in our discussion to explain it that way. But here we're going to show there's really three different forms of the PID algorithm. And then we will go through some considerations, which are just sort of footnotes, if you will, on reset, windup, and a few other things that I think we can wrap into this one segment. Now, there's three forms. I keep talking about three forms of the algorithm. There's a parallel form, there's a standard form, and there's a classical form. We as ABB have all three. The parallel form is with our infinity, harmony, the Bailey control system. The standard or non-interacting or ideal form of the PID algorithm is referred to, it's used in the master, the 450, we call it a PIDCon. And then the classical interacting is actually the Mod 300 or the Taylor series. So in the book I have a whole list of different manufacturers, and I still recommend after this discussion you'll be able to look at the pictures and the algorithms and go to the manufacturer's book and see what type it is. There's been so many, I've seen this happen more than once, where somebody will have had a particular brand of controller and they got really good at tuning and setting up the tuning numbers. And so they were getting ready to upgrade to a new vendor of controller. And so the expert in tuning said, well, I know what to do. He copied all the PID algorithms or parameters from the old controller and put them all in the new controller. When the plant started up, things oscillated all over the place. They brought in the tuning expert and he goes, they're the same numbers I've always used. This system's broken. And that's not the case. Is the algorithm changed. And when the algorithm changes or the mode changes or you go from one vendor to another and they've changed, and even today what they're doing is you can have one controller could be set up. Now it's an option. You say, which form do you want? Which that makes it real fun. Used to, you could tell by looking at a vendor, you could tell what kind of control form you had. Today, you actually have to go in and look at the attributes of the controller to see which mode that it's in. I was at one place where they had one manufacturer and I dumped out their mode. Half of them were parallel, half of them were standard, and the controls were all a mess. And the E&I staff just said, we don't get tuning. The same numbers on the same loop, they don't work. And it's because mathematically they were being used different. So this section we're going to give you a block diagram. I'll show you how to read that. I'll show you the equation. And I'll show you a simple conversion. It really doesn't matter. As long as you know what form you have, you can work in one form and then convert it to whatever else you have. And we have algorithms, we have tuning tools and different, I think in our loop tune application, I think we have 40 or 50 different tuning manufacturers. So you specify the manufacturer and it calculates the tuning numbers for you. We have spreadsheets and you'll be able to make a lot of them off of this talk. So let's get into it. This is what's called the parallel form of the PID algorithm. The reason it's called parallel is, well, look at it. Each of these lines are parallel. Is the path's the same? So we have an error. The error, if there is no integral or derivative, it goes straight through here. That kind of makes sense. Proportional gain times the error, okay? Or if you're going to use integral, you have the error goes through the integral on the error, or derivative. You take the derivative times the error, and then there are three independent paths. In other words, one gain doesn't impact the other two. They are completely independent, okay, so they're parallel. And when you look at the math, now this is where people kind of freak out, but this is just the math, and I recommend comparing this to your user document for that particular controller, and you can tell. So this one's showing the mathematical representation. So this is the proportional, this is this middle path, proportional. P, capital P is proportional gain. This is an ISA thing again. If it's a lowercase p, it's process. If it's a capital P, it's proportional. So we have a K is a gain. So we have an E is error, and U is the output of the actuator. So the output of the controller is a function equals a gain multiplier times the error, an integral of that area over time. So it's an integral gain. Usually when I hear someone say I have an integral gain, I'm leaning in the direction of parallel, because integral gain is just a number. There's no repeat time. Usually when they're talking about repeat or reset, they're not talking about the parallel form. And then derivative. So you're simply taking the derivative of the error with respect to time times the derivative gain. So there are three independent paths. I'll talk about pluses and minuses here in just a minute, but that's the parallel form. The standard form of the PID algorithm, if you look at the block diagram, here's the parallel, then you go to the standard. They literally just slid the gain back to where it gets applied to all three lines. So you can see here in the math, you've got these parentheses. So they literally took the control gain out or applied it to each one, in other words. So you have the control gain times the error, and then you have the control gain times the error, and the integral of that, control gain. So it looks like it's really messy. This is called the standard, and it's actually called the non-interacting. He's like, well, how's that possible? Well, it's sort of a trick. You know, remember we talked about the effective integral time? When you hear things like repeats per minute, notice the now the gain for the control gain is actually time. So you're like, well, how is time a gain? Well, again, time is how long it takes for the integral value to reset or repeat the original proportional kick. This is the standard form of the algorithm. And so you're defining an amount of time. And same thing with the derivative time. It's like, how far into the future do I expect my error to be? And then I'll compensate for that with my proportional action. So it's just a different algorithm. And if it's interesting, I thought it was interesting to dig back into the original manufacturers, the big powerhouses, the three that I've mentioned. Were three different companies that are now, together. But you could look at the old pneumatic instrumentation and see the baffles and the nozzles, and it was amazing works of art that these guys built these mechanical devices. And so they started with proportional, then they added integral, then they added derivative, and then they realized, well, we could probably reduce the complexity of our hardware by taking the baffles apart and having so it literally was how the market was introduced, was the mechanical devices that made PID. They didn't always used to be a bit on your display. They used to be big, clunky mechanical devices, and it was how they were built. And so they just, when they went they just copied their mechanical devices into an electrical device, and then they standardized on three different forms. The third form, this looks really freaky when you first look at it, it's like, well, shoot, this is what's called the classical mode of the PID algorithm. But if you look at it, what it's got here is, notice it's got two parentheses. So what's happening, and I like to speak of it in terms of, if you look at this, set point minus value is the error. The error goes straight through here. So this is the current error, all right? Now the derivative, remember what I said about derivative is trying to predict where the error is going to go. So this branch, the error and the derivative, it's saying, well, here's where you're going to go, is the predicted error. So then it adds where it thinks you're going to go with where you're at and says this is your compensated error. Now, PI algorithm, you work on it just like you always did. So I can almost see these fellas when they come up with a PI algorithm mechanically that worked just fine. And they say, well, your competitors have added derivative, and they're like, oh, so they just added a module in front. And so literally it matches the way the hardware was built. But this is a nice one. If you have second order processes, I'll just give you a little bit of a hint. Second order processes, this is an easier dynamic to work with. Most of the time, if you look at this, if you set your derivative to 0, what does this become? So take a look at that. If you set the derivative value to 0, this path goes away. Now if I go back and look at the standard, if the derivative is set to 0, notice that what's left is this. Standard and parallel are the same if the derivative time is set equal to 0, which most of the time it is. So when you reduce the complexity of the problem by setting derivative to 0, there's only really 2 controllers you have to worry about, parallel and standard, because standard and classical would be the same. Now that's what I want to talk about here. This is just to show that sometimes, usually what they'll say is repeat per second. As soon as you hear the term repeat per second, they're talking about standard or classical. If it's just a gain with its unitless, it's usually parallel because it's just a number, it's a multiplier. Time is not part of it. When time is part of it, it's usually standard or classical. But it can be confusing because it's either in repeats per second, or if it's a gain, or it's the inverse of that, seconds per repeat. And it gets even more fun because, like the Mod 300 was working on very slow dynamics. So they standardized the integral time in minutes. So if you're working in a chemical industry that had a 30-minute time constant, you just entered a 30 for your integral time. Well, the master, they worked on drives, a lot faster type stuff, and so they went with seconds. So if you had a 30-minute time constant, you'd have to enter, you know, whatever that is, 30 times, what's my brain stop, 30 minutes, 60 seconds, 1800 seconds or something like that. That's why there's a magnitude of 60 different if you get your units wrong. So make sure that whatever your time constant units are and your integral time units are matched. That's very important. Now, I want to talk a little bit about the conversion. If you have a parallel, and let's say you're really good at standard, but you're working on parallel, or you're really good at parallel and you want to go on standard. I want to just show you a little bit of the differences, and it's not that big a deal. You can always convert one to the other. So here, since derivative is just not used very much, I'm going to assume that we have this block diagram. So you can see I'm parallel. The gains parallel to each other. They're gains. And then here's standard, which we just talked about, is the Kc is multiplied through. Now, remember we talked about repeat time. In the terms of math for a standard, this is a standard interpretation, okay? Remember the equation? Kc multiplies through, that's what I'm showing here. So the first thing you do is you multiply through the gain. So the proportional part is Kc times the error. The integral part is Kc divided by the integral time, okay? Now, when does the integral part equal the proportional part? What has to happen to time? Well, if we look at this, again, don't let me lose you. If when time builds up to equal the integral time, they cancel. Boom, boom, and I'm left with the integral part, Kce, is equal to the proportional part. That's really for some people, math clicks, some people pictures click. I showed you the pictures before, this is the math. And when I saw that, it's like, oh, together, I get it. Reset time, it's mathematically just when the two parts are equal. Okay? Now, this shows, I showed you this example earlier. Notice I now have the line drawn. Remember I was showing this is the proportional kick. How long does it take for that proportional kick to repeat? Well, what if the proportional kick is this big? Notice they all take the same time. Okay, that's what's nice. That's why they call it standard or non-interacting. In other words, you can change the proportional gain and you don't have to change the reset time, or the integral time is a function of the process gain. So you really kind of want to set it and forget it, and then you can adjust the speed with the proportional gain. Now on the parallel side of the fence, look what happens. Here I have a constant gain and I'm going to adjust the proportional. So notice that the proportional gain is proportional to the step change, but look at the integral time. Literally by increasing, this is what's kind of funny about a parallel controller, is if you increase the proportional gain, you slow down the regulation capability of that controller. In other words, it takes longer. So you may get a good set point change and it takes forever to get back to based on a disturbance. And you're like, well, that's weird. So one of the things I see people that have learned to tune by feel, they'll have hands. I'm doing this like when I started, everything was knobs. So you had a proportional integral knob. And so you were actually playing with the P and the I knob. So if you wanted to change the speed, you had to change them both. Well, on a standard algorithm, literally once you set the integral time, you don't ever have to change it again, and you can change the speed with proportional only. On a parallel algorithm, if you want to change the speed so that you have the same effective integral time, you have to not only increase the proportional, but also increase the integral. That's the only difference. And once you figure that out, it's not that big a deal. But if you don't know, you can actually tune it one way for set point change and have a very poor performance for set point for disturbance regulation. Now, this is what I want to show you. The next step here is the math that shows how you could convert from one form to the other. On the left is the standard equation. On the right is the parallel equation. So the first thing you have to do is multiply through. So you can see the control gain is multiplied through. Then you compare like terms. So you can see here I take the proportional part, and so what falls out of that is, that's what's interesting too, between a standard and parallel, the gain, the proportional gain is the same. They have the same meaning. Matter of fact, they're interchangeable. Where the fun starts is on this side, the integral part. When I take the integral component and make them equal, I can see here that there's a relationship that the control gain divided by the integral time is equal to the integral gain. It's not a difficult conversion, but if you don't know that, you're just guessing. And there's a lot of different conversions, and I have more talked about in the book, but I just wanted to show you some examples. Put some numbers in and play with it and see what you get. Now, to finish this off, I want to talk a little bit more about some considerations when you're talking about PID, parallel, standard, classic. And there's just a few other things that you need to think about when you're talking about setting up a controller. One of the ones that when we first started was called Windup. Imagine yourself trying to, if you had a spigot and you were trying to open the spigot, but let's say the spigot had 10 turns from stop to stop. But once you got past the second turn, the velocity of water coming out of it didn't change. But because you wanted the bucket to fill up faster, you kept spinning. So from turn 3 to turn 10, nothing happened, okay? So you're now outside the control range of that particular device. Now you're filling your bucket and the bucket gets full. You're like, oh, now it's full. To shut it off, you have to now turn from 10 to 9 to 8, 7, 6. You have to turn all the way down until you get to turn 2 and 1. So what's likely going to happen? Your bucket's going to overflow. That's the best illustration, or not best, it's an illustration that tells you what windup is. And if you trended it, it would look like this. Is here, if someone dumps some water out of my bucket, and I say, I need to fill this thing up. So I start opening it up, and I keep opening it past the area that is effective, okay? Then all of a sudden it starts to come back. It's filling it at the max, even though it thinks it's up here, and it starts to cut it down. So all this time that it's making a change, I end up on the other side. And that's called reset windup. Because remember, the integral control will keep driving the output as long as there's an error. So here there was an error, it kept going, even though the output was out of gas. So on a lot of controllers, they'll have a high-low actuator limit or a 0 to 100, and it will do what's called a reset windup or anti-reset windup, which will just stop the output from going any higher. So for example, it says I can't go beyond 100, so I'm going to stop. And then what that would have done is once the measurement started to come around, it could have acted faster and avoided this negative effect of windup. So most controllers today, it's just a given that you're going to have anti-reset windup. You usually have to have limits and say you stop integrating the error if the output exceeds a maximum or a minimum. Okay? Now, derivative, what we talked about, it's a lead action, and it's used to make the PI respond faster. That's great in theory, but in practice, it's kind of difficult. The successful use of the derivative term, it really depends on the type of process and if there's noise on it, and that's what I'm going to show you here. This is showing a simulated case where 3 different phases. In the first, off control, the actuator's not moving, so the measurement's just wiggling along. So I kind of got a noise signature. Then I put the PI algorithm on, and you can see it sort of jerking around, and I get a little bit tighter. It's sort of like snap the piano line, boom, and now I got noise. That's actually, there's a whole bunch of control theory in that one statement, is you want noise, you want the signal to be removed. So that's what a PI algorithm does. So now you throw derivative on. Look what happened. Derivative starts jerking around the output because I got a lot of noise. Remember, it's predicting in the future where you're going to be. So every little change, this would say the derivative value is too high. So what do? I just want to point that out is when you use derivative, people say, well, I need that derivative kick. Boom. I'll tell you in the next section that you can get that with PI by itself. Derivative by itself, if you don't really know how to utilize it, you can burn up your actuator or the test points. Now, fast-moving processes or processes with noise are bad candidates for derivative because you have to condition those signals before the derivative action's worked on. And that's what I want to talk about here. Imagine our friend the step change, especially a step change. What's the slope of a step? I was here. The slope is infinite. Well, it's really tough to make an infinite change in your actuator in no time. So what people do, that's what happens here, is you can see you've got a step change, so you go from a slope of 0 to a slope of infinite to a slope of 0. Noise is a lot like that. So you're predicting an infinite slope, so they set their derivative time so small, so well, I'm just going to go a little bit up on the infinite curve, and that's what causes your output to twitch around. So what people have done is, oh, we'll just solve that. We'll put a derivative filter. The old days, they called this preact or a preact filter. It was a reservoir to try to slow down the twitchiness of the measurement. But the filter literally would smooth it out. So now if I look at the derivative, this is what it would look like. I don't go, in this case, I went up to infinity and back. In this case, it's just a little bit of a curve. Okay? So that's what the derivative filter is designed to do. I think, I shouldn't say that absolute, but every one I've seen, if derivative's used, it will also ask for a derivative filter. A lot of times the default for the derivative filter is 1/10 of the derivative time. That's, in some cases, it's hard-coded. You put in a derivative of 1, you get a derivative filter of 1/10 of a second. Some places allow you to adjust it. But you will almost always have a derivative filter if you're going to use the derivative. And it would look like this. So you'd have a little derivative filter that comes in and so that you're filtering the signal to try to get the noise out, to get the signal characteristics. In other words, you're wanting to slow the measurement down. That way the prediction can work a little better. I was trying to envision, if you can imagine, the points, like I drew earlier, a point, and then extend the slope on every one, and then if that represented how the process moves, your derivative is probably going to work. If you have a real slow move, remember I talked about the slow moving road? A derivative would predict where you would be if you didn't do anything. So the slower and more predictable the measurement, derivative has a chance. When there's a lot of noise, then you put a great big old filter on, but a filter doesn't just take out the noise, it actually slows the process down. So you can it's almost a wash. If you use derivative with a derivative filter, it almost doesn't do anything. That's why you have to be careful. But what happens if I change the set point? What happens if I do a step change in the set point? If I step the set point, I get an error. It looks literally just like this. This is like I change the set point. Well, do you really want to crack the output every time you do that? Most of the time, no. If you're doing that, most people will give you the option to say, do you want your derivative to act on the error, or do you want it to act on the measured value? If you act on the error, then whenever the guy changes the set point, you're going to get that big crack in the output. Well, that's bad on the actuator. So then they're like, well, I want to do it on the measured value because the measured value just naturally doesn't move. So typically, if I'm going to use a derivative, I want the derivative on the measurement with a derivative filter. But I just wanted to illustrate those are other settings that you have to deal with. Is it reverse or direct acting? We talked about that in an earlier video. You talk about the anti-reset windup. Usually you have ability to set that based upon limits. You have a derivative filter that is a function of the derivative time, and then you have to decide if you want it on the measurement or on the error. When we started, when I hear people say it's just tuning, I'm like, boy, there's a lot to tuning. You have to know the process. You have to be able to identify the process characteristics. You have to understand actuators and instruments and that block diagram. Then when you get to the core, the brain of the controller, it takes an error. We convert the error into an action. And the error is a function of the set point minus the measured value. The action is a function of the type of controller. Is it standard? Is it parallel? Is it classical? The type of process, is it first order, second order, overdamped, underdamped, critically damped, tank, integrating? That defines the attributes of the error, but it still boils down to magnitude, duration, rate of change. The tuning parameters are a function of the type of controller. And then the last ingredient is how do you want it to respond? Do you want it to respond fast? Do you want it to respond fast, slow, overshoot, undershoot? You get to define that. That's what's called tuning. There's so much more than just throwing in some numbers and seeing what happens. There's a process to follow. And it starts with the process. It starts with understanding the controller. And next, we're going to glue those together. And that's what's called tuning. And we're going to cover that in the next video series.